Okay, now for what we have in the case of linear transformations, and let's say that if we have v and w to be vector spaces, where we're going to have the function t, the transformation, as we go from the vector space v to the vector space in w, is going to be a linear transformation of v into w when the two properties below are true for all that we have for vectors u and v in the vector spaces v, and for any scalar c, we're going to have the transformation of the sum of the vectors is going to be equal to the sum of the transformations of the vectors. And we have, second, that the transformation of the scalar multiple of vector u is going to be equal to the scalar multiple of the transformation of the vector u. And we'll be looking at determining whether the following transformations will be linear or not. And let's say that for what we have in going from vector space R3 to itself within the transformation, and we're determining whether the following transformation we have is linear or not. And here we have the transformation of what we have in x, y, and z is equal to x plus y, x minus y, and z. And to determine whether this is a linear transformation or not, again, we have with the characteristics that determine whether we have a linear transformation. Again, you're looking at the transformation of the sum of the vectors u and v is equal to the sum of the transformations of the vectors, and also the transformation of the scalar of u is equal to the scalar of t, or I should say c, times the transformation of vector u. So in terms of the methodology, okay, so for u and v, now we are in three dimensions here. Okay, so we have for u, okay, we can say that is equal to u sub 1, u sub 2, and u sub 3. And for v, we have v sub 1, v sub 2, and v sub 3. And just setting things up here. Now for the sum of the vectors u and v, okay, so we have u sub 1 plus v sub 1, u sub 2 plus v sub 2, and u sub 3 plus v sub 3. And now we have just in line with the transformation with the variables x, y, and z, and just creating a parallel. Okay, now we need to find out what the transformation of the vector u is going to be. And again, we have for the transformation of u, again, we're looking at the transformation of u sub 1, u sub 2, and u sub 3. And think of x, y, and z being respectively represented by u sub 1, u sub 2, and u sub 3. So for x plus y, we have in correspondence u sub 1 plus u sub 2. For x minus y, I have u sub 1 minus u sub 2. And for z, I have just u sub 3. Same thing with v. The transformation of that, we have the transformation of v sub 1, v sub 2, and v sub 3. So we got that with the v sub 1 plus v sub 2, and the difference between v sub 1 and v sub 2 followed by v sub 3. And now for the transformation of u plus v. Now again, we have u plus v. You have this set of vectors and carrying over to what we have here. So we got the transformation of u sub 1 plus v sub 1, u sub 2 plus v sub 2, u sub 3 plus v sub 3. And just looking at what we have here. Okay, so you could think of, in this particular case, as x being represented by u sub 1, v sub 1, y by u sub 2 plus v sub 2, and z by u sub 3 plus v sub 3. And just for x plus y, so you're adding the first two sets of vectors together. For the second component, I'm taking the difference between those same first two sets of vectors. And in the case of what we have in the case of corresponding to z, okay, so looking at u sub 3 plus v sub 3. And so for the transform of u plus v, so if I combine the like variables together, so I have u sub 1 plus u sub 2 plus v sub 1 plus v sub 2, followed by u sub 1 minus u sub 2 plus v sub 1 minus v sub 2, and at the end I have u sub 3 plus v sub 3. And to look at whether the first property we have is going to be satisfied, whether the transform of the sum of the vectors u and v will be equal to the sum of the transforms of u and v. And so for what we have for the transform of u plus v, again, I have this set of vectors, and for, again, the transform of u, I got u of 1 plus u sub 2, u sub 1 minus u sub 2, u sub 3, and for the transform of v, I have v sub 1 plus v sub 2, followed by v sub 1 minus v sub 2, and then followed by v sub 3. And if I add this set of vectors together and arrange, it's going to turn out that for what we have both sides to be equal to each other. Okay, and so that is going to check out. Okay, and then just looking at scalar multiples. Okay, so now again, the transform of u, you got the sum of u sub 1 and u sub 2, followed by the difference between u sub 1 and u sub 2, and then we have u sub 3. Now for the transform of the scalar c times u, so just looking at it item by item, so I had the transform of c u sub 1, c u sub 2, c u sub 3, and again that's going to carry out to the sum of c u sub 1 and c u sub 2, followed by the difference between c u sub 1 and c u sub 2. Then I have c u sub 3, and then just condensing, say have factoring out c, so I have c times the quantity of u sub 1 plus u sub 2. Then I have c times the quantity of u sub 1 minus u sub 2, followed by c u sub 3. And for the scalar multiple of the transform of u, and that's going to end up as c times what I have for the transform of u and distributing throughout, and this will come out to the same for what I have in this particular case. So it turns out that this relation is equal, and it's going to turn out that for 11, okay, that is going to be definitely yes. Now let's say that looking at what we have for this problem to see if we have a linear transformation within R2, okay, and so we have the transformation in x and y is equal to x and 1, and looking at fulfilling what we have in the requirements for a linear transformation to see if both conditions will be met, and just kind of taking what we have in x and y to the variables u and v. So again, if we let u be equal to the set consisting of u sub 1, u sub 2, v with v sub 1, v sub 2, and I'm limiting to two variable expressions since I'm looking at R2. And for u plus v, so I got u sub 1 plus v sub 1, u sub 2 plus v sub 2. And now, again, we had the given transform t of x, y is equal to x and 1. And just looking at what we have in the realm of working with the variables u and v. So we can say that u sub 1 is mapped with x, u sub 2 with y. And so we have x goes to x, u sub 1 goes to u sub 1. But now as y is changed to 1, u sub 2 is changed to 1 in the transformation. Same thing for what we have for the transform of v. Okay, now you can think of v sub 1 corresponding to x. Okay, so x goes to x in what we have for the given transform. Okay, and so in like fashion, v sub 1 repeats, whereas in the case of just like y and u sub 2 change over to 1, same thing happens to v sub 2. And for what we have in the case of the sum of u and v, okay, if I take the transform of this, and it's going to turn out that, okay, the sum of u sub 1 and v sub 1 would correspond to x, and u sub 2 plus v sub 2 will correspond to y. And again, just we had the repetition of the first set of items, so we have u sub 1 plus v sub 1, whereas for the second set, that goes directly to 1. And just for what we have in the setup, now we have in terms of whether we had the transform to be linear, and this be whether we have the transform of u plus v equal to the sum of the transforms of u and v. Okay, so we got for the transform of u plus v, so I have this set, transform of u, I have u sub 1 and 1, that of v, I have v sub 1 and 1, and so we have on the left, again repeating, so I have u sub 1 plus v sub 1, 1, to the right, okay, I have adding together the first components, I have u sub 1 plus v sub 1, second components, I'm going to have 1 and 1 added together, and guess what? The sum of 1 and 1 is going to be 2, and that is not going to match perfectly with the transform of u plus v, where I have the constant at 1. And so in this particular case now, you're going to have the answer to be no. But I just want to carry this over in terms of the scalar multiples. Now again, we have for the transform given, again, t, or the transform of xy is equal to x1. And again, just going back to what we had worked out earlier, the transform of u is equal to u sub 1 and 1. Now for the transform of c times u, okay, now that's going to be the transform of c u sub 1, c u sub 2, and guess what? So just as x goes to x, c u sub 1 goes to c u sub 1, but c u sub 2 is going to be parallel to y, which changes over to 1, and c u sub 2 changing over to 1 is the fate that awaits this term. And for the scalar multiple c times the transform of u, so you're looking at c times u sub 1 and 1, and you're going to have distribution in this particular case. So c times the transform of u is equal to c u sub 1 and c. And in terms of whether we have the transforms involving the scalars to be equal to each other, and so we have with the transform of cu, that was c u sub 1 and 1, whereas for c times the transform of u, we ended up with c u sub 1 and c, and we have a mismatch between 1 and c at the ends, and so we have an imbalance. So for what we have in this problem in that particular regard, again, and this is already verified by trying to test out the first part, and it does turn out that this particular transform that we have here is not linear.